Welcome to this explainer on pointers in C and C++. Today, we're going to demystify one of programming's most powerful, but honestly most misunderstood concepts. Look, if you're tuning in, you probably already know how to write basic code. But maybe you've hit that infamous wall where memory management suddenly becomes manual. Well, that is exactly what we are going to conquer today. Let's just put it out there. If you have ever felt completely lost staring at these symbols, you are definitely not alone. I mean, looking at an ampersand or an asterisk placed seemingly at random in a codebase, it can make C and C++ feel like an alien language. But stick with me here, because today we're going to translate all of that into clear, logical concepts. Here is our roadmap. We are following what's widely recognized as the standard progression for learning these core components. 1. Understanding memory and pointers. 2. Pointer arithmetic and arrays. 3. Functions and advanced pointers. 4. Managing dynamic memory. And 5. Avoiding common pointer mistakes. All right, let's jump right into Section 1, Understanding Memory and Pointers, laying the foundation. To really get this, you have to think of your computer's RAM like a really long street. On this street, your variables are the houses. Every single house has an exact address, right? That's its memory location. And the data, like the number 25, well, that's the value actually living inside that house. Every time you declare a variable, the computer is basically building a house, giving it an address, say address 1000, and putting your data safely inside. So, keeping that whole street analogy in mind, a pointer is simply a variable that holds one of those street addresses instead of the actual house contents. It's really that simple. Instead of holding the number 25, a pointer holds the literal location, like address 1000, where that number 25 is stored. Now, to find out where a variable actually lives, we use the ampersand, which is the address operator. By sticking the symbol directly in front of a variable name, you extract its exact memory location in the system. It's literally the equivalent of looking up a house in a directory to find out exactly what street address it was built on. If you ran a print function on this, you'd get a hexadecimal output, something like 0x61FF08. Though keep in mind, the actual address is going to differ depending on your specific system. Conversely, we have the star, or the dereference operator. Think of this as the key that lets us open the door at that address and access the value inside. When you place a star in front of a pointer, you aren't looking at the address anymore. You're looking at the actual data living at that address. You use this when you want to either read the data or permanently modify it. Okay, time for our first critical safety warning. Sometimes a pointer shouldn't point anywhere yet. To keep our program from just crashing out of nowhere, we explicitly point it to nothing using null, or NNullPTR if you're writing in modern C++. The rule here is incredibly simple. Never try to open a door that doesn't exist, and absolutely never dereference a null pointer. Moving right along to Section 2, Pointer Arithmetic and Arrays, Navigating Memory. So when dealing with arrays, pointers can actually step through memory automatically. In C and C++, an array's name is actually just a pointer to its very first element. If you tell a pointer to increment, moving from one integer to the next, pointer arithmetic automatically accounts for the specific byte size of the data type. You don't have to calculate the bytes yourself. The compiler knows exactly how far to jump to hit the start of the next item. All right, Section 3, Functions and Advanced Pointers, Taking Control. Here is an absolutely crucial point. Passing a pointer to a function allows you to permanently alter the original data. This is completely different from passing a standard variable. Usually, when you pass a variable to a function, you're just passing a copy. But when you pass a pointer, which is known as pass by address, you hand over the direct memory location. The function goes straight to that address and changes the real data. So you can update a variable from 10 to 100 instantly, and it stays changed. And get this, we can even have pointers pointing to other pointers. You'll usually see this written with 2 asterisks. While this might sound like a weird riddle, storing the address of an address is actually highly useful. It's used all the time in advanced memory management and when you're dealing with complex, multidimensional data structures. Now, to maximize your flexibility, we have void pointers. These can store the addresses of literally any data type. You just have to remember to typecast them before you use them. On top of that, we have function pointers. Because remember, functions live in memory too. Function pointers let us store their addresses, which is absolutely essential if you want to create callbacks and event-driven systems.
Which brings us to Section 4, Managing Dynamic Memory, Building on the Fly. Depending on which language you're using, you'll use different functions to request raw memory on the fly. C relies on functions like malloc to grab a specific block of memory using its byte size during runtime. C++, on the other hand, gives us the slightly more streamlined new operator. But here's the thing. Both give you incredible, raw access to the machine, and both absolutely require you to manage that memory manually.
And that brings us to the absolute golden rule of pointers. Whatever memory you dynamically allocate, you must explicitly release it back to the system. You are just borrowing space from the computer. In C, you use free. In C++, you use delete. If you fail to do this, your program will just slowly hoard memory until the entire system crashes. Definitely not what we want.
Finally, Section 5, Avoiding Common Pointer Mistakes, the guardrails. There are 4 absolute worst mistakes you can make when working with pointers. First, uninitialized pointers. These point to random, unpredictable garbage memory. Second, dereferencing a null pointer, which, like we said, will instantly crash your application. Third, forgetting to free memory. That causes those dreaded memory leaks we just talked about. And finally, using dangling pointers. This means you're trying to read or modify data at an address that the system has already reclaimed.
So how do we code safely? Well, always initialize your pointers immediately when you create them. The moment you free a block of memory, set that pointer to null right away so it can't cause damage later. Try to avoid unnecessarily complex pointer arithmetic. And honestly, if you're working in modern C++, just utilize smart pointers whenever possible, because they handle a lot of this cleanup automatically behind the scenes. As the saying goes, master pointers, and you'll understand how computers really manage memory. Pointers are literally the foundation of operating systems, compilers, databases, and game engines. By understanding addresses, dereferencing, and dynamic allocation, you aren't just writing high-level code anymore. You are directly commanding the hardware. So, having covered all this, do you finally feel ready to truly command your computer's memory? Thanks for joining me on this explainer. Keep practicing, and happy coding.